Hello again. Another lesson in Calculus 1, and a very important one today. So we're going to talk about the rate of change, the definition of rate of change. So we've already talked about the motivation for the definition, and today we're going to actually give the full definition. So this will be fun. Let's get started. Alrighty. There we go. So we're going to give a precise definition of the rate of change. We've already talked about the rate of change of a function, and we've given a couple of ways to intuitively think about it. You could give another 15 ways, but we gave 3. The slope of the line tangent to the function's graph. We had some numerical evidence that said that although delta y over delta x becomes a meaningless fraction when delta x is 0, nonetheless, if you look at the numbers as delta x gets smaller and smaller and smaller, gets nearer and nearer to 0, you have a sense that there's a meaning to what it's talking about, the slope of that line. Likewise, when the function gives the object's position, you have some sense that there's a meaning to the velocity of that object. And finally, we talked about the function's local expansion rate that we'll talk about soon enough in the upcoming chapter, actually. So we have some sense that it all has some meaning. I want to focus on in particular the slope of the line tangent to the function's graph. It's not the only meaning of what we're doing today, but it's the one that you run across most often. So of course you can see I've drawn in here that there's a line that it goes through 2 points on the function. And one of them is the anchor point, a comma f of a, and one of them is a plus 1 comma f of a plus 1. That's this one here. And we've calculated the slope of that line, and it turns out that the slope of that line in this graph is 1.5. And now, of course, what we're going to do is we're going to let the delta x assume smaller and smaller values. So here I go with delta x equals 0.5. Did you see that the dot slides down the curve? Dot slides down the curve. One more time. The red dot slides down the curve. And I've calculated that the slope at that point of the red line is 1.75. And now it's 1.875. And now the red dot is delta x of 0.1. So that is to say it's a plus 0.1 comma f of a plus 0.1. And you find that the slope of that red line, the secant line, is 1.95. And of course, when delta x is 0, the expression f of a plus delta x minus f of a over delta x it's undefined. It's, you got a 0 in the denominator. Nonetheless, I think we have a sense that if you follow that very next step, that you let that red, think of it as a bead on a string, you let that red point slide down, then you're looking at a sensible value of 2. So looking at smaller and smaller x's showed us the slopes of the secant lines trending to the slope of the tangent line, which we look at these numbers and say it's 2. Come on, it's 2. All right, so the idea of trend arose, and we spent a couple of days defining limits and working out the rules for limits, and we also illustrated the definition of limit with continuity. But now we're back, and we're ready to define the rate of change because we've got a precise meaning for trend. Okay, so here we go. There's the f of a plus, I'm going to use h instead of delta x just for this is an awkward expression to keep writing over and over again, and it makes parentheses. And so we're going to write h. It's become traditional to use h sometimes. We're going to write h in the place of delta x, but it's all obviously the same thing. There's f of a plus h minus f of a over h in the place of f of a plus delta x minus f of a all over delta x. Okay, so that's called a difference quotient because there's a difference on top and it's a quotient. So a complicated name. And so that leaves us ready. We take that the instantaneous rate of change of the function is the limit as h goes to 0. Limit as h goes to 0 of the difference quotient. And we can think of that as a limit as h goes to 0 of delta y over, I should have said delta x goes to 0. Limit as delta x goes to 0. Where's my pen thing? There we go. Delta x. There we go. Got confused by my own writing. Delta y over delta x. And we have that expression. And this is a very important definition. Very important. So exclamation point. It's sort of a monumental step in humankind's long, slow climb from the primordial ooze kind of stuff. I mean, just extremely important, and we're going to spend a lot of time on it because it's important to understand it and to understand all of its ramifications. Okay, so that's the instantaneous rate of change of the function f at the anchor point x equals a, the anchor number x equals a. We'll sometimes also call that the derivative of f at a, but more on that later. The notation for all that, you can write all that in a number of ways. Here's the way we will most often use. We'll put a little prime, so you would read that out loud as f prime of a. Here's another way that we will often use dy dx, and the vertical bar you might read as evaluated at t equals a. One advantage of the notation that I just circled is that the delta y over delta x becomes, as x becomes very small, becomes dy over dx, and the changing the deltas to d's indicates that you've switched to extremely, extremely tiny, infinitesimal numbers. But we'll talk about that more later, but that's some advantage to the third notation. Both notations, each notation has some advantages. We'll most often use the prime notation. Okay, so having done the definition, next up is to work through a number of examples, as many examples as we could comfortably fit in one lesson. So I took a typical function is not supposed to be a complicated function, just supposed to be sort of complicated enough to illustrate the points. So g of x is 1 minus x squared, and the anchor number is a equals 3. So here I directly applied the definition right there. That's straight, copied from the previous page. Of course, you got to expand g of 3 plus h and g of 3. G of 3 doesn't. Nobody ever says to me, I have trouble with the g of 3. That's all obvious. But the g of 3 plus h is a thing that people could get wrong. So the following would be wrong. It would be wrong to write 1 minus 3 squared plus h, some version of that. That would be wrong. You got to square both halves of the, you have to square the entire term, so that both halves get written underneath the square. The 3 plus h both get written as part of the square. And of course, when you write them both, you got to expand that, and it turns out to be there it is, 3-term expression, 9 plus 6h plus h squared. And don't forget there's a minus sign in front, so there's going to be some kind of subtracting. But nonetheless, the mistake that you'll see people make is the 3 plus h, they don't square the entire thing. So we squared the entire thing, did it right. When you square 1 minus 9, that's negative 8. When you expand that, you get a whole negative 8 there. And I noticed that this says 1 minus 9, so there's a negative 8 on the left-hand side, and there's a minus a negative 8 on the right-hand side of the numerator. And so there's a certain amount of canceling happens on the top of that fraction. It's not a coincidence. When you do these, very often there's canceling between the two terms. And when the smoke clears, I end up with a minus 6h and a minus h squared. Do you see that the minus here became in front of the 6h and also in front of the h squared? And so I got minus 6h minus h squared. Okay, so we're asked to take the value of this limit, and it seems like we made some progress. The difficulty with this limit, the sort of technical object to overcome here, is that it is a fraction of two, happens to be a fraction of two polynomials. It's a fraction of two things, and the limit of the denominator is 0. The limit of the denominator is 0. So the technical thing we will have to overcome when we do these problems on this slide and subsequent slides is that you've got to somehow make it so that you're no longer looking at a fraction with a denominator whose limit is 0. So you got to be looking for some kind of manipulation that gets rid of that 0 in the bottom. Oh, dog is barking because she hears me talking. Oh, it might be time for treats. So in this case, it's not a difficult manipulation. You can see what you do. You factor h out of the numerator, and now I'm going to cancel those h's, cancel the h's, and minus 6 minus h no longer has a 0 in the denominator, so I just plug in and get minus 6. So again, the difficulty in evaluating this expression right here is going to be that you've got a limit of 0 in the denominator, and so we can't just simply plug in for all the obvious reasons. Okay, so as we move forward, we will be expanding the definition as we did here, but we'll always keep an eye on what happens to the denominator. Do you get a limit of 0 in the denominator? And is there some algebraic way to work around that? We started off by motivating this work here, with numerically. So I just want to tie back to what we saw before. What we saw before was that they were delta x's at the time and they're h's now, but we're taking these to be closer and closer to 0, sometimes positive, sometimes negative, taking them to be closer and closer to 0 so that we're looking at an interval that is closer and closer to the anchor number. And then we looked at delta y over, again, it was delta y over delta x earlier, but now it's delta y over h. And we asked ourselves, what's the trend? What's the trend? And come on, if you looked at this numerical example, you would say the trend is to be -6. And of course, the trend fits perfectly with what we found algebraically. Okay, so this ties back to what we were talking about before. It all fits together. It's, you have the sense that things make sense. All right, it's an important, very important idea. I can't overemphasize the importance of the limit of the difference quotient. So, I don't want to do one example. I want to do a number. Don't want to do 100, but want to do enough that a person feels like, all right, I see what's happening. So t squared plus 3. T equals 2. Okay, so there I am. There's the limit of the difference quotient. When you expand the 2 plus h inside the expression for f, again, the mistake that people make is that they will write something like 4 plus h. What happened is they squared the 2, but they didn't square 2 plus h. All right, so we're not making that mistake. 2 plus h squared, and don't forget the plus 3, and 2 squared plus 3. When you square the 2 plus h, you get this expression right here. And when you square you're looking at 2 squared plus 3, 4 plus 3 is 7, and so that's that over there. So we have a 3-term expression, and it's got, I see here, if you look at the algebra, do you see the 4 and also the 3? So there's a plus 7, and it cancels with the minus 7. And I mentioned last time, and we'll keep seeing it over and over, you often see cancellation between the left and right-hand sides of the numerator, the difference quotient. Often see that. What's left is 4h plus h squared over h. Good, 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 good. And again, we're seeing the pattern that I cautioned you about on the previous slide, that you've got a fraction here, and the limit of the denominator of the fraction is 0. So again, we've come to this case that we've already considered a little bit extra, where you have a limit of a denominator. It comes to be 0, and so we know that we're looking around for some algebra that will get us out of this pickle. So you cancel the h's. That is to say, you factor h out of the numerator, and there it is, factor h out of the numerator. Please don't factor h just out of the 4h. You got to factor h out of both of the terms in the numerator. Again, sometimes a person in a hurry will make that boo-boo, factor h out of both terms, and then you cancel the h's, top and bottom, and you're left with a limit that no longer has h in the denominator. So you just plug in, and you're just looking at 4. You'll remember also that we spent a certain amount of effort remarking that when you take the limit as h goes to 0, that h never actually equals 0. And that's what gives me the justification for canceling h, because as long as h doesn't equal 0, this fraction and this, it's not really a fraction, are equal. All right, so anyway, so there we go. The algebra was to somehow figure a way to get rid of that h in the denominator, and I ended up with a 4. And again, the notations that summarize what happens is we will typically write f prime of 2, remember the 2 up here? F prime of 2 is 4, or we might write dy dx evaluated at t equals 2 gives 4, or df dt dy dt, forgive me, evaluated at t equals 2 equals 4, or df dt evaluated at t equals 2 equals 4. All three ways to write this. We'll actually have some other ways to write it too, but the manipulation that we're seeing is a direct application of the definition. Okay, so we saw two that were relatively straightforward. There was just an algebraic step in the middle where you had to factor out h, so not very hard. So obvious next step is to get ready to do homework problems that are a little bit harder than what we just saw. So here we go. F of x is 1 over x, and we're looking at the anchor point of 2. There's the limit of the difference quotient, so that's straight the definition exactly applied. And when you plug in a 2 plus h into f, you don't get 1 over x. You don't get 1 over 2 and then plus h. That's not right. Instead, you get 1 over 2 plus h. All right, I said it enough now. Maybe I won't say it anymore. 1 over 2 plus h minus 1 over 2 over h. And again, we find ourselves with that h in the denominator. We can't directly apply the limit because we have a 0 in the bottom of the fraction. The limit of the denominator is 0. All right, so we're looking for a way to get rid of that h. And I think kind of the natural thing, since we have a fractions in the numerator, we have a 1 over 2 plus h and a 1 over 2 in the numerator, the natural thing is to get a common denominator in the numerator. So a little bit complicated. Get a common denominator in the numerator. So here I go. This is the 1 over 2 plus h, except I multiply top and bottom by 2. And this is the 1 over 2, except I multiply top and bottom by 2 plus h, because I want a common denominator of 2 times 2 plus h. That's how you get a common denominator. All right, so let's see. A common denominator is 2 plus h, so there, common denominator of 2 plus h, I see it. And then on the numerator, there's a 2 and a minus 2 plus h. And so when the smoke clears, the 2's cancel, and you just got the minus h. So this is h is in the numerator of the numerator, and h down here is in the denominator, so those fellas cancel. And so I've just got the minus 1 over 2 times 2 plus h. And how does that solve the problem? I still have an h in the denominator. The goal is not to get rid of the h in the denominator. The goal is to get rid of having a limit of 0 in the denominator. That's the goal. And I no longer have a limit of 0 in the denominator. If you plug h equals 0 into this denominator, you don't get 0. You instead, of course, obviously, get 4. So we've solved the difficulty of having a limit of 0 in the denominator, and so what we end up with as a summary here is that the rate of change of this function at this anchor number is minus 1 over 4. Okay, so again the pattern is you start with the definition, start straight from the definition, limit of the difference quotient, and I emphasize how important that definition is. And then the sort of algebraic manipulation is you've got a limit of the denominator is 0, and if you can find some way to make it so that the limit of the denominator is not 0, then you're home free. And we did find some way. We got common denominators and factored and sort of stuff, and we ended up with minus a quarter. All right, so having done a somewhat more complicated example, we have a somewhat better sort of overview of what's happening. You start straight from the definition, and you look to see, do you have a limit of 0 in the denominator, and if so, you're looking for some way to arrange for that not to happen. Okay, the last example for that is like the homework, and here f of x is x squared. Excuse me, f of x is square root of x. Sorry, f of x is square root of x, and the anchor number is 4. Directly apply the definition. Square root of 4 plus h. Again, I said I wouldn't say it anymore. I'll say it one more time. You put in square root of 4 plus h is not correct. What's correct is square root of 4 plus h. And here, and again, we find ourselves with the problem we always find ourselves with, which is the limit of the denominator is 0. So we've got to find some way around that. Now, I know nobody is going to say to me, right? Nobody's going to say to me, I'm going to cancel those h's. Nobody's going to say that, right? You can't cancel, you can't work inside the square root sign like that. That's just simply not going to happen. Okay, so instead we're looking to do some algebra, but it's not the obvious thing. So instead what we're going to do is it's more complicated. That's why it's the last example, is I have a square root of 4 plus h and a square root of 4 with a minus sign between them. I'm looking to somehow arrange to get the h out of there so that I can cancel with the h on the bottom. And so what I'm going to do is I'm going to multiply that square root of 4 plus h and the square root of 4 with a plus sign between them, because I know the difference of two squares, a minus b times a plus b. That's what I've got. I've got an a minus b over here and an a plus b over here is a squared. That's going to get rid of the square root. Minus b squared. That's going to get rid of the square root. So I'm looking to leverage that familiar algebraic expression. All right, so there's the a squared right there. There's the a squared, there's the b squared, and the minus sign between them. And what happens on the bottom is you get an h times this. It's not a very pretty expression, square root of 4 plus h plus the square root of 4. And let's see what happens. Well, in the numerator, there's a 4 and a minus 4, so you're just left with an h. Good, 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 good. And the denominator, bit of a mess, bit of a dog's breakfast. That's absolutely true. But the h's cancel. Ha 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 ha. H's cancel. We're home free because look, the limit of the denominator is not 0. Again, we're not looking to get rid of the h in the denominator. We're looking to make it so that the limit of the denominator is not 0. And we got that. It was a little complicated, and it took a bright idea, but nonetheless we got it. So now I can plug in h equals 0 to the numerator. There's nothing to do there, but you plug in h equals 0 to the denominator, you get square root of 4. Square root of 4, you add them together, you get a total of 4. So you end up with a rate of change of this function. Rate of change of this function at the anchor point, at the point of interest, is 1 over 4. Okay, and of course the homework is going to ask a person to do a number of these, some of them a little more algebraically complicated than others, but they all have the same basic idea where you have to get rid of that limit of 0 in the denominator. Some of the homework also asks the person to apply a meaning to all the algebraic expressions that we're generating. It's important to not lose track of the fact that all this stuff means something. So one of the things that the homework will ask a person to do is to find the slope, is to find the equation of the tangent line. So for that we need the slope of the tangent line, and then I'm going to plug in. So let's see, f of t is t squared plus 3, and the point is 2 comma 7. If you plug 2 in, you do get 7. And I want to find there the rate of change, and we know how to find the rate of change because we did that earlier. It so happens that the rate of change is 4. We did that a couple slides ago. How would you use that to find the tangent line? And the answer is you plug it into this. This is sometimes called the point-slope form of the equation of the line, and you should memorize this. So this is the point-slope form. And you should memorize it. Just simply memorize it. Going to use it, 100 times between now and next month. So you should memorize it. And you simply plug in y minus 7, x minus 2, and there's the slope of 4. That's a perfectly correct answer. That is an equation of a line. It's a criteria for membership in a line. If somebody says, I got x equals 97 and y equals, you absolutely can plug it in and say yes or no, it's on the line. So that's great. But I will say that people often have been raised on sort of y equals mx plus b, expressing y as a function of x. So often people want to transfer this, to translate this form of the equation of the line into the one that they're familiar with, and the sort of the real one. People say, what's the real equation? So I simply moved the minus 7 and y minus 7, I moved it over to the other side. See, I added 7 to both sides. Multiply through by the 4, so you say 4x minus 8, and there's still the plus 7, and negative 8 and plus 7 makes minus 1. And so there we go, y equals mx plus b. I drew the graph because I got a computer and I'm determined to use it. There's the point 2 comma 7, and there's the line with slope 4. And I mean, it sure looks like the line tangent to the curve, right? It all is what we were talking about in the first day or two when we were trying to motivate the rate of change of the function. It all looks exactly like that. So we found the way to calculate the things that, a couple of videos ago, we were just sort of pointing to and saying it should go like this. Well, it does go like that. Okay, one for practice. So as usual, I like folks to practice during the video because you can straighten out any problem you have. So I'm going to ask you to pause the video and try it. Take out a piece of paper and try it on your own. Find the equation of the line tangent to 2x squared plus 3x at the anchor point, at the anchor number a equals 1. And your plan should be, I'm going to find the slope by taking the limit of the difference quotient. That's step 1. And step 2 is to plug in to the to the point slope form of the equation of the line. Okay, so pause the video and give it a try. Okay, so I found the rate of change. Here is, I directly applied the definition. There it is. That's the limit of the difference quotient. you get some algebra, and anybody can lose a minus sign, but it's not really very complicated. And there's a plus, do you see the 2 times 1 and 3 times 1 makes 5? So there's a plus 5 and a minus 5, and so what's left when all the smoke clears is 7h plus 2h squared over h, and we know how to deal with that case. You cancel the h's here, factor the h's out and cancel them. 7 plus 2h, and you get 7. And again, the mistake that people will sometimes make is they'll sort of cancel this h and this h, and they'll forget that. No, don't do that. Don't do that. That's a mistake. Instead, you have to factor h out of the entire expression as here. But in any event, we get a 7. So the slope is 7, and then the point slope form of the equation of the line is going to be y minus y1 equals slope. Sometimes people call that m, x minus x1. You plug into that, and it gives you the equation of the tangent line. So I did that. I plugged in, and I got y minus 5. Y minus 5 equals 7 times x minus 1. Where did I get the 5 from? Well, I simply plugged 1 into this formula. That's it. And then for the y equals mx plus b form, I moved the 5 over and did the algebra. So again, there we go. Here's the line with slope 7. Pretty steep, and it goes to the point 1 comma 5, which lies on the curve. Okay? All right. Now, one more thing I want to talk about. At the very beginning of today's discussion, I said that the rate of change, the instantaneous rate of change of the function at the anchor number, is sometimes called the derivative, and I want to briefly discuss what that's about. Again, the homework will refer to that. So when you do a number of these problems, I picked f of x equals x squared because it's not very complicated, and I'm going to do a number of these problems at different anchor numbers. So anchor number 1, etc. And when you do that, you start to see a pattern. So there's a pattern in the rate of change, and let's go through it. So if you find the rate of change of f of x equals x squared at the anchor number a equals 1, you know what's happening. I'm going to take the difference quotient and do the algebra. Limit of the difference quotient and do the algebra. So here it is. There's the limit of the difference quotient, and I did the algebra, and the algebra is pretty familiar at this point. You end up canceling the h's, and there we go. We got an answer of 2. Okay, all looks pretty, all looks pretty routine at this point. Of course, the person needs to practice it on the homework, but nonetheless, pretty routine. A equals 2. Same thing, exact same thing. Compare it, exact same thing. Limit of the difference quotient. Look at what happens here. Compare these two. Cancel the h's in both cases, and you end up with very similar results. In other words, there's a pattern. 1, 2, 3, 4, 5. They all go the same way. Well, to a mathematician, the phrase "they all go the same way" means there's a formula there. So I'm just going to apply this. I'm going to apply the pattern in 1 and 2. I'm not going to do a equals 1, a equals 2. I'm just going to do a. And I'll find the formula. So here we go. And of course, what's happening here is the limit of the difference quotient. It's just like the above stuff. There's a certain amount of algebra that's just like the above stuff, just like the above stuff. I know having 2 letters instead of 1, having A and H instead of just H, is somewhat a step up in complexity, but it's not brutal, especially when you have a couple of numerical examples to guide you. Cancel the H's. We remember canceling the H's. Plug in H equals 0, and you end up with twice A, and that fits. This is twice A, twice A. That's right. And this is twice A. That's right. That's right. So the pattern is, when f of x equals x squared, the pattern is that and you try the anchor point at A, the pattern is that you end up with a rate of change of twice A. So there's a formula for the rate of change at x equals A. And the formula is that f prime of A is twice A. Right there. F prime of A is twice A. That formula is derived from the formula for f, of course. You started off with x squared, and then you did some algebra. Not awfully complicated, but a little bit complicated. You did some algebra, and you ended up with a formula. That formula is derived from the formula for f, so it's called a derivative formula. And we're going to spend the next, month and a half going through derivative formulas in various cases. Okay, all right. So very important day, but also kind of kind of fun because it's fun to make vast amount of progress on a day. We've been setting this day up for a number of lectures now, but we're ready, and it went very smoothly. So very good, very exciting. And of course, next up is to do the homework in this section. Okay, great.